Hello, my name is Brandon, and today I'll be presenting my project, which is degradable spirocyclic polyacetal-based core amphiphilic assemblies for encapsulation and release of hydrophobic cargo. So stimulus-responsive polymers is particularly interesting for developing degradable nanomaterials due to the fact that we must take into account the acidity within our bodies, such as our stomach, which has a value of 2, all the way to all our intestines, which range between 5 and 8. Was brought significant attention due to the fact that their cleavage yields non-toxic products are acetals. So a good starting material to work with are hydroxybenzaldehydes, which are derived from lignin, which is the second most abundant natural polymer on Earth and the most abundant source of bio-based aromatic feedstocks. Now, of the various acetals formed, what has yet to have been reported are spirocyclic polyacetals, which will confer rigidity to the polymer backbone in order to enhance its thermal stability. So the overall objective of this project is to synthesize spirocyclic polyacetals, in which upon the simultaneous encapsulation of a mild drug and self-assembly will form micelles. And then from there, under slightly acidic media, the micelles will degrade and the cargo will be released at a specific target site. For the synthesis, these spirocyclic units are formed via acetylization of 4-hydroxybenzaldehyde and pentaerythritol in a strong acid, in which from there, the end groups will be attached with alkyne units so that they can be clicked with 2 hydrophilic polyethylene glycol azides, based on the 2 different repeat units, to form the overall amphiphilic spirocyclic polyacetal, which is initially confirmed by nuclear magnetic resonance by the singlet at 7.8 for the triazyl ring, the singlet at 5.2 for the CH2 adjacent to the triazyl ring, and the singlet at 5.4 to indicate the acetal peaks. So size exclusion chromatography is used to determine the molecular weights of the polymers, where we can see that they range between 16,000 and 73,000, which does indicate that polymers did form overall. From there, differential scattering calorimetry is used to determine whether or not the polymers are amorphous, meaning no structural order or organization, or crystalline, which contains structural order and organization. Now, to determine whether or not they are amorphous or crystalline, we first see whether if there is only a glass transition, what we do see in both of these cases, which indicates that both polymers are amorphous. From there, we study the degradation of the polymers just to give us an idea as to how efficient they are before studying the nanoparticles. Where we can see that after 3 days, that we see a simultaneous disappearance of the acetal peak, shown as A, and the simultaneous appearance of the aldehyde peak, which is shown as A prime. From there, we study the self-assembly by studying its size of the nanoparticles and morphology using transmission electron microscopy and atomic force microscopy, where we can see in both cases that spherical micelles were formed, and the sizes range between 400 to 430 nanometers in both scenarios, which were in good agreement with one another. From there, we studied the release of the encapsulated drug, which in this case was a nile-red dye, by studying the fluorescence decrease profile that after 4 days, an overall 75% release was achieved. But yet under neutral pH, we see a similar pattern, which we hypothesize is due to the fact that the micelles do not contain a complete inner hydrophobic core, but rather a mixture of hydrophobic and hydrophilic, causing a leaky nature. And lastly, we studied the cell toxicity and cellular uptake. So first is the cell toxicity based on the charts that at various buffers and low to high concentrations of the nanoparticles, that 90%, at least 90% of the cells were alive, which this can be supported by the visual aspect by the merging of the live cells in green with the dead cells in red, where with the exception of the sapoin buffer, that in the phosphate buffer and the nanoparticles at the highest concentration, that we say that there is little to no cell toxicity present. And then from there, we studied the uptake of the nanoparticles, shown in red, with the cells, which are shown as green for the cytoplasm and blue for the nucleus, and that overall, the uptake was successful. So what we can take away from this project is the amphiphilic spirocyclic polyacetals were successfully synthesized. The encapsulation and release of the model drug under physiological conditions were successful as well, along with little to no cytotoxicity and promising preliminary cellular uptake. As well, a possible future application is its use as a coating material. Thank you very much and have a good day.